The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and thank you for joining us in today's webinar on maximizing product life with SolidWorks Simulation. My name is Vernon Tang with Intercad, and I'll be your host for today's event. Just before we go any further, I just want to do a sound check to see if everyone is hearing me fine. If you could just reply using your chat panel. Just need to get this out of the way, and then we'll start the webinar. So can everyone hear me? Is everyone hearing me fine? Okay. All right, so let's get underway. This webinar, you will discover SolidWorks Fatigue Simulation. We'll also review a fatigue theory and see how SolidWorks can actually address and solve this complex problem. Now, without further ado, let me introduce you to our guest speaker today, Alex Henry. He is the SolidWorks Technical Manager for Australia and New Zealand. Over to you, Alex.
Thank you, Vernon. Okay, so good morning, good afternoon, wherever you are in Australia and New Zealand. Today we'll be talking about maximising product life with SolidWorks Simulation. On the agenda today, we'll be talking briefly on fatigue and how we can predict it. And next we'll show an example of how we can use the tools in SolidWorks Simulation to reduce physical testing. And finally we'll summarise. So fatigue. Why are we talking about vacuum cleaners? When you purchase a vacuum cleaner, what things do you think about apart from the price and performance? Is it important to you if you are offered as a customer a warranty, a year, 2 years maybe, a maintenance or servicing schedule, replacement parts if needed? A lot of companies will employ these items so that they can increase their income stream, especially the replacement parts. Do you offer a warranty with your products? Do you know how strong your parts are, how long they'll last? I'm sure many of you do. Do you provide maintenance schedules to your customer? All these can be predicted with fatigue. Today we're going to talk about fatigue and maximising service life and predicting product life. So before we go further, I'd just like to ask, what tools do you use today to validate your design service life? And I'll just give you a couple of seconds here. So is it physical testing, hand calculations, standalone FEA, integrated FEA, that's where the FEA forms part of your CAD system, or none?
Okay, so some interesting numbers here, Alex. 83% look at physical testing, 17% for hand calculations, and another 17% for standalone FEA.
And the integrated FEA, is there?
No one.
Oh, that was both the FEA.
Yeah, yeah.
No one with integrated FEA. Okay. So the responses are pretty much to be expected where physical testing dominates, but as there's been advancements in the last few years, we can change this a little to reduce physical testing, which of course will save you time and money. So about fatigue. We're all aware of the types of fatigue as engineers. Now, just a refresher for those, we can design for a heavy load to failure, so our parts will be designed for strength, or in the fatigue situation, we design for a cyclic or unsteady load to failure. And these are generally repeated lower loads, and in this case we're designing for life. As engineers, we're all duty bound to ensure our mechanical failures do not occur, but sometimes we make doubly sure that they're not going to do that. So potentially some over-designing gets done. So fatigue. I thought I'd illustrate the impact of fatigue by this image here of Mike Tyson punching. I know that if I was connected with this puncher, this is what I think about, is that my face would get absolutely crushed. Now if I look over at Grandma on the other side, you can imagine that you know, she might tap you on the nose and it might sting a little. You say, Grandma, please stop that. And then she hits you again and you say, Grandma, please stop that. But you're not really suffering too much. But what if she could hit you 100 times? Maybe 1,000 times? Well, probably she would fatigue first. But in a theoretical world, that grandma would probably pummel your face just as badly over that time. So what is fatigue exactly? It's the progressive, localized, permanent structural change that happens to a subject to produce fluctuating stresses and strains that culminate in cracks or complete fracture after a significant or sufficient number of fluctuations. So in this example here, we can see a bolt that's sheared through. It would have started with an initial surface crack, which is visible here, and then ratcheted out into our beach marks, which will then progress across the part to the final fracture region where the bolt becomes two parts. Now what's interesting to note here is that how much of the part has actually failed prior to the bolt finally fracturing. And that's an indication of the low load, but the repetitive cycle that went through that caused that fracture. So basic concepts. Fatigue is caused by repeated loading through constant amplitude, rotating machinery, so turbines, vehicle shafts, rotating shafts in machinery, and it's shown that you might have a constant amplitude where the magnitude of the load and unloading is the same in both. And as we said, it's typical of a rotating shaft. Now the variable amplitude example is a little bit more random in nature, and it might seem that way, but there are blocks of loading and unloading that occur regularly over time. A typical example might be a offshore drilling rig where it's exposed to the wind and waves and cycles in the ocean, or a car suspension in this case. So on with the basic concept. A material's fatigue strength is characterized by its stress versus cycles curve, or SN curve. And in an SN curve we can see a low cycle area, high cycle, and then infinite life. And down the bottom we can see the cycles. So around 10 million cycles here for a particular material might guarantee infinite life. And we have the low cycle region, which is dominated by strain, and then the high cycle region, which is dominated by stress. So these are tests that have been carried out in the lab, and you can see the smattering of the statistical data on that graph. So these curves can also be used inside SolidWorks Simulation Professional. Fatigue cracks grow due to the stress range of the repeated load, not the maximum load, as you might think. Now we have a stress range here. You can see the 0 point and the positive and negative ranges of that axis, and it's the stress range, which is the maximum stress minus the minimum stress. But a positive mean stress is also very important. What this does is reduces the fatigue life of a part. So increased fatigue life is good, reduced fatigue life is bad in general, depending on what you're doing with your components. So if there was a negative mean stress, your part would be under compression most of the time and would see less damage, whereas in the positive range, the crack is open more of the time. So predicting fatigue with SolidWorks Simulation Professional. SolidWorks Simulation uses the same SN approach to predict high cycle fatigue in metals. And the calculation is done in two stages. First we will perform a linear study, and this will give us an alternating stress rate, and then we'll define the fatigue study, which will reference that linear static study to use its stress state. So the next question is service life a design challenge for your team? Now I may have said yes and no here, but there is also another option there, which might be that you don't see these challenges, whether you don't think you need them or whether they're just not necessary with your product. So there's the NA option there as well.
We've got 100% yes here, Alex.
Okay, so the NA is not really a problem in this case. It's not surprising that the majority of respondents said that it's an issue, and in this case it's everybody. So interestingly enough, the rule of thumb says it's 80% of medical failures are actually due to fatigue. Sorry about that. So today we'll be looking at this steering bracket, which is part of a wheel assembly. You can see it there on the right, and the bracket we'll be looking at is on the left, as you can see here. So I keep pressing the wrong button. What we're going to do today is have a look and see whether the part will break through our general loading conditions, and then through fatigue conditions we'll determine when will it break or when it will break, and also from these results will we be able to determine our service life. And we'll use some historical data to work that out. So our goals today are to design for strength, and we're going to use a factor of safety of 2, so our maximum load is whatever we decide it to be, and then we're going to basically make sure that it can handle double that load, which is a standard engineering practice for some components. And finally, we'll design for life to last 1,000,000 cycles. So if those of you who are unfamiliar with simulation, and I believe many of you don't use integrated FEA or FEA to that point, use physical testing, the setup is a few different simple steps where we restrain the component to simulate a real-world environment. We'll apply a fixture on the back and also apply some fixtures that simulate bolts, and we'll apply a 5,000 Newton side load, a remote load in this case, because we don't have that component purely for speed in this instance. We could use an assembly, but I'm more interested in the quick results in the first instance. Then we'll mesh and solve that, which will do the calculation, of course, which will generate our results. So we'll review those results and modify as necessary, make design changes inside SolidWorks for each of our stages. And the results will look something like this, where we have a maximum iteration of our stresses and a factor of safety count there, and also a deflection. So, will it break? Let's get into showing you what happens inside SolidWorks. Now I can see you've got my bracket on screen, and there it is. We're inside the SolidWorks environment, and all we need to do from here is create a new study where we can choose a static simulation, as you can see there, and maybe give it a name. So design for strength. So this information, when someone else opens this file, if we need them to, they'll understand what we're trying to achieve with that. So it's informative in that way. So on the left-hand side, we have our design simulation setup. We have our little bracket item with its material assigned, and we have some fixtures we need to assign. So we're going to assign a fixture to that back face. And I'll just wait for the screen to catch up there. And we're also going to assign those bolt hole locations to emulate a real bolt. Well, not a real bolt, but emulating that bolt. And next we'll then insert that remote load, which we discussed before. So just add these two faces here for where that joint is going to sit. And we're going to use a coordinate system which sits in the center of mass for where that bolt would have sat, and we're also going to apply a load down the left-hand side here. If you can see, we're just applying a load of 5,000 newtons, and all the information is displayed nicely on screen for us. So we can see the annotation for our bolt, and all that's left to do for us now is to run that calculation. And it seems that I have missed something here. Let's have a look at our different items there. Okay, we've got our load. Alright, so for some reason I didn't quite get that load in. Okay, so apologies for that. Problem between chair and keyboard, as they like to say. So let's run that analysis, and here we go. In just a couple of seconds our results have been given to us. So on the left here we can see that a yield strength at 206 megapascals has not even come close to being touched. Our maximum is 93 megapascals, and at our lowest we're at 145 or 146 kilopascals. Our displacement we can see is 0.003 mil, and our factor of safety, as we can see there, well, we're well within, well over our 2, or just over our factor of safety of 2. Now that's fine, but we need to have a look at that fatigue study. So let's have a look at a new study now, and this time we're going to choose fatigue. Okay, so we've got a fatigue test here, and I'm going to just type in some information again. Design for life, or design for cycles, say. And we want this part to basically never fail. So we need to add some, add an event to this. And I see my screen is actually a little bit slower, but hopefully we're at the right area now. You can see that under my add event constraint there, we're going to add 1,000,000 cycles. So I can easily just type in that number that I wanted. And also this 1,000,000 cycles means that this bracket is going to be subject to someone turning the wheel hard, full lock to the right and full lock to the left. So effectively we're traveling around 1,000,000 corners. So that event is added, but we still need to add some fatigue data to our part here. And we can derive that from a material which is in our custom database here, and this is a carbon steel, so we're just going for a generic ASME carbon steel curve there, and we're going to apply that to our part. So we've got all the information we need, and all we need to do now is just to run that study. It's incredibly quick, so you've got your results straight away, and we can look and see our life cycle here. That's our top level there. That was what we wanted to predict. 1,000,000 cycles of this part, and we can see on screen, if you once I've zoomed it in there, that there is a blemish around those sharp edges on the top and the bottom, and we know that any kind of surface finish problem is going to be a stress concentrator. So the best way to do that, to solve that problem, is to make a design change. Now you'll see on the life cycle part, we can immediately see that it's going to last a little over the third of the design life that we wanted to. So any crack is a bad crack. So we need to go back to the SolidWorks environment, and of course it's fully integrated. So we just want to make a design change there. Maybe thicken up this web. So this number will actually draw the bottom faces downward towards each other, which will thicken up that. And we're also going to increase the radius of our web here, which will then make that a little bit better for us. So after we've made a design change, we need to also, I said about rounding off those edges. This is another way that we can reduce fatigue by smoothing off any sharp edges or notches. And we'll just put that fillet in there, and we can see that design change is being made. So after a design change has been made, we need to remesh that component. Remesh and solve. So that's all done. Our stresses have dropped down to 70 megapascals. The displacement is slightly lower, 0.0029, and our factor of safety is up towards the 3 mark. So actually it's quite strong. So let's have a look at the design for cycles that we created and run that. And the results this time, okay, we can see with these changes, now everything is in the positive 1 million range. So we've really designed for the infinite life in this case. So let's switch back to SolidWorks. Let's switch back to the presentation and will it break? So we determined in the last step that we analyzed 2 designs, and through the intuitive interface we're able to validate the strength of both these designs, including when it will break. And we determined that, made a design change, and within a couple of minutes we had our results. So the fatigue analysis allowed us to calculate the design life. So now just a couple of helpful tips. Loading is generally separated into constant amplitude events and variable amplitude events, and when we're dealing with fatigue we need to think about the loading and what sort of events we need to run. We didn't have much information on the SN curve, so if you've got it, use it. But if you don't have it, you can use some sort of generic data to run the test, and in the case of this design we use that ASME approximation. And it's also important to understand how an interaction can exist between multiple load cases to set up an accurate study. Now, of course, we can do that in SolidWorks simulation, professional simulation in general, sorry. It's also important to understand how the interaction can go, it's also important to remember about our mean stress, and the material data might be different between case studies. So also the loading conditions might be different, where we've got, instead of steering a full lock to the left and a full lock to the right, we're actually steering from a half lock to the right and steering straight again. So you need to think about how these correction methods need to be used for accuracy. So question 3, how accurate do you know your product's in-service loads? Can everybody hear me?
Got some results coming in. Wow.
So
it's quite diverse.
Is it? Okay, so the questions were, we approximate it, we have historical data, we measure from a physical prototype, or we use industry standard test cases.
Okay, we have, sorry, Alex, just something very interesting. 57% says we measure from a physical prototype. 43% says we approximate it. Another 14% we have historical data. Another 14% on we use industry standard test cases.
Okay, so in this case we're looking at the majority of people use approximation or measuring physical prototypes, followed by the historical data and industry standard cases. Is that correct?
Yeah, physical prototypes followed by approximation.
Oh, okay, rightio. So how do you determine your product service life? And most of us know where our peak load is going to be so that we can estimate the cyclic loads. So can we determine the service life of our parts? In this study what we're going to do is use a combination of industry case study and the approximation which we used previously. So what we need to think about here is this car is now going to be modified to be based on a race car. We have some information about the load cycling during the period of one race, or maybe let's call it a lap. And so we're going to mix the historical data and use that 5,000 newtons we set up previously. So can we determine service life? Let's switch back to SolidWorks to look at the last point in our case study here. So I think you should be able to see on screen my part from before, and we need to now create another study. And under our fatigue analysis here, you can see down the left-hand side, we're going to choose a variable amplitude history data case study, and we'll call this design for service this time. And now what we want to do again is to add an event, and from that event, this time we've got the option to select a curve. Now this car is, this information will be relevant for one life cycle, but we actually want to determine maybe through 72 laps how this part will perform. So we're going to get a curve from some existing data from the American Engineering Society, and grab that from a curve like so. Now they have some information for load history on bracket, suspension and transmission. So the Automotive Engineers American item there. Okay, not quite sure what's going on there. But we also have the option at this point to enter not at this point, sorry, but you can bring in your own data, your X and Y coordinates, and yeah, I've already got some data ready so I can use that. And we can go ahead and view that curve to see what the actual data contains. So it's also unit-based, so I need to just modify this, otherwise it's going to be a little too heavy. And we're also going to type in that value for 72 repeats of that same case study. So all our information is there, and we just need to run that again. And our results are immediate, so setup is really the hardest part, and it's quite simple as well. So our life cycle, we can see here that actually it will last quite a long time, this particular bracket, but portions of it where even where we change the geometry are still going to suffer. So it says here that after about 2.7 repeats of this same conditioning, that this part will probably start to initiate a surface crack. So it's probably good if we replace this after two laps. So let's switch back to SolidWorks simulation, the presentation, and we'll continue on with this discussion. So what have we got? In the last example, we used real world data to change the application of the bracket and accurately understand how the component's service life will be. And we saw how it would behave as well. And through this process, we were determined that the bracket design would have been replaced every 2 races. This making the bracket heavier might have been good for its life, but might have been more expensive in the long run, and maybe a cheaper, lighter bracket being replaced every 2 races is more of the thing we might have. So we were able to visualize component behavior and also predict a maintenance schedule based on this. So the different things we went through are will it break, when will it break, and can I determine service life? And through the static simulation, we were able to validate our design, and you saw we did that quite quickly, as well as the fatigue analysis where we calculated design life based on some theoretical scenarios, and then using real-world scenarios and estimations, we were able to visualize the behavior and predict the maintenance schedule. So question 4 here, and we're not really going to respond to this one, but I'm not going to discuss this one too much, but basically what's your general interest in SolidWorks simulation? We saw some, if you've seen some things that might be interesting to help you design your fatigue life or service life, then maybe this is interesting to you. So are you interested? Beginning investigation, evaluating, etc. And we'll just wait a couple more seconds, and Vernon, you can just let me know when I can move on to the next.
Yeah, you can move on.
So some helpful tips. Basically, to get accurate results, you need to put good stuff in. So good stuff in equals good stuff out. And if you've got load histories for your design, then even better. Remember the importance of surface defects, so notches and sharp edges in your design, and always incorporate smoothing of this. I'm not talking any rocket science here. You've all heard this before. This reduces your stress gradients, and recognizing that many factors can improve resistance to fatigue. So post-geometry, peening, coating, cladding, painting, and chemical inhibitors can, shot peening, can assist with your service life. So mitigating fatigue. Fatigue cracks start at locations of high stress, as we saw, and basically all we need to do is reduce those stress concentrators. That's one basic thing we can do in our everyday work. And a positive mean stress means that we're damaging the fatigue life, and negative mean stresses are actually beneficial. We can create compressive residual through design or manufacturing processes, including shrink fits, shop peening, and autofrettage. Now, would you like further information from us? And I'll just let you answer those polls. And Vernon, you just let me know when it's time to move on.
Sure. Okay, you can move on.
Okay, so back to our trusty old vacuum cleaner. We saw in the two examples that fatigue analysis can predict the service life of our components. We had the 72 race item there, but you know that could have been 1,000 days that you wanted the part to last for, or 2 years, or another sort of timeline that you might want to involve, so that you had an understood maintenance or servicing schedule. So designing components for service life would enable you to provide a warranty. And because you can predict when your parts will fail, you can also offer a maintenance schedule to your customers. How important is that to you? And finally, you can provide another income stream if you can offer some sort of replacement parts for your customers. So in summary, predicting fatigue enables you to design your service life and reduce service field failures, and also predict maintenance schedules. You can stop over or under designing your parts. You've got the knowledge there in the simulation to achieve that, and you can also investigate the effects of material selection on product life as you are using a parallel process with your simulation tools. So thank you for attending. I hope you enjoyed the presentation. Any questions, you'll have to put them over to Vernon and the team. And I guess, Vernon, are you able to just take control? Yes, you are.
Yep. All right, thank you, Alex. If you need more information on SolidWorks simulation, please visit our website at the following link. Or if you've got questions or inquiries and you need to contact us, please use the numbers on the screen or send us an email at info@intercat.com.au. So thank you for attending. Hope you found this session beneficial to you. To questions, I said, either call us or send us an email. Thank you very much for attending. Thank you.
Thank you.